Have you ever wondered why the earth pulls everything toward it, whether it's an apple falling from a tree or a person jumping off a chair? Well, it's not magic. It's gravity, and the force behind it is described by Newton's Universal Law of Gravitation. Sir Isaac Newton proposed that every object in the universe attracts every other object. Yes, every single object, no matter how big or small. This force of attraction is what we call the gravitational force. And this law doesn't just apply to apples and Earth, it also explains how the moon orbits Earth, how planets revolve around the sun, and even how galaxies hold together. Let's now look at how Newton described this mathematically. According to Newton's law, the gravitational force between two masses depends on two things, their masses and the distance between them. The force is directly proportional to the product of the two masses. That means if you double one of the masses, the force becomes double. It is also inversely proportional to the square of the distance between them. So if the distance doubles, the force becomes 1/4. The formula is F equals G into m1 into m2 divided by r squared, where F is the gravitational force, G is the gravitational constant, m1 and m2 are the two masses, and r is the distance between their centers. This formula helps us calculate the force between any two masses, whether they're two stones or two planets. Let's now talk about the most interesting part of the formula. The gravitational constant, Gg, is a number that makes the equation work across all distances and masses. It remains the same anywhere in the universe, no matter the location, temperature, or material. Its standard value is 6.67 into 10 raised to the power -11 Newton meter squared per kilogram squared. Now, here's something amazing. If we take two 1 kilogram masses and place them 1 meter apart, the force between them will be exactly equal to G. So you can think of G as the force of attraction between two 1 kilogram masses placed 1 meter apart in vacuum. Gravitational force is always attractive in nature. It always pulls masses toward each other. And here's something important. It acts along the straight line that joins the centers of the two masses. Now remember, just like any other force, gravitational force also follows Newton's third law. That means if mass 1 pulls on mass 2, then mass 2 pulls back on mass 1 with equal force in the opposite direction. These two forces form an action-reaction pair, acting on different bodies, equal in magnitude but opposite in direction. Let's try a simple calculation to understand how small the gravitational force is between everyday objects. Suppose we place two masses of 1 kilogram each exactly 1 meter apart. We apply the formula F equals G into m1 into m2 divided by r squared. Substitute the values. G equals 6.67 into 10 raised to the power -11, m1 equals 1 kilogram, m2 equals 1 kilogram, and r equals 1 meter. So, force equals 6.67 into 10 raised to the power -11 newtons. That's a very, very small force, which is why you don't feel the pull from your water bottle or your pencil. Gravitational attraction between small objects is practically negligible. Let's now try a much bigger example. The gravitational force between Earth and the Moon. Mass of Earth equals 5.96 into 10 raised to the power 24 kilograms. Mass of Moon equals 7.36 into 10 raised to the power 22 kilograms. Distance between them is about 3.80 into 10 raised to the power 8 meters. Plug these into the formula. F equals G into m1 into m2 divided by r squared. When you substitute all values, the answer comes out to be around 2 into 10 raised to the power 20 newtons. That's a huge force. And that's what keeps the Moon in orbit around the Earth. So, although gravity is weak between small objects, it becomes enormously powerful when huge celestial bodies are involved. Let's wrap it all up. Newton's universal law of gravitation tells us that all objects in the universe attract each other. The force is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. The gravitational constant, g, helps us calculate the force, and its value stays the same everywhere in the universe. We learned that gravitational force is significant between large celestial bodies, but too small to notice between everyday items. This law forms the foundation of planetary motion, satellite orbits, tides, and even the structure of galaxies. I hope you now have a clear understanding of the invisible thread that connects every object in the universe: gravity. See you in the next session, where we explore more forces that shape the cosmos around us.